So whenever you start out Aspen, you're gonna get a screen that looks something like this. And you just press new simulation. And now we are in the Aspen environment. So the first thing that you're always going to need to do is list out your components. You'll usually know what this is in your senior design, that those will be given to you. But for this case, we are going to be looking at benzene and toluene, which if they have known names like this, you can just type them out and it'll generate the information. If you're working with some weird chemical like 1,2-dimethyl something or whatever, a lot of the times you're not gonna be able to type that in. But they have different methods in the molecular structure section where once you add a name, this information will be left blank, and you can add that and even draw the chemical structure of it, and then it'll generate and estimate properties for it. But these are known ones, so all the numbers will be taken from databases that are already within Aspen. So we'll also look at acetonitrile and let's look at acetone, water. Yeah, so we'll look at these for now. So once you list out all of your components, you're going to need to go to the methods section. So good thing about Aspen is that it'll actually tell you pretty much everything that you need to do. So if you look, it's hard to see on the big screen, but there's a little circle with half of it's red, the other half's white. And if something is not done yet, it'll say required input incomplete at the bottom, and it'll show you where you need to put in some input before it can start doing calculations. So if we go to that, that's where we have to select our methods. We'll usually just leave this one to common. And the base method for this, I'm going to select an RTL. Sometimes you could select something like Ping Robinson or something else. An RTL is usually the one that you're going to be using in senior design. So we can select that. We can click the drop down because we could see that it's still showing up red. And here we have our parameters that we need to click. Our binary interaction. This is something that you're going to have to do pretty much every time. You just click it. Now the properties input is complete. So you can go to the top here and press the little play button to run the simulation for the first time. This will generate all the binary interactions, which at the top here, we have pure and binary. Those are the main ones that you're really going to be using, especially binary. But in binary, if we click that, we'll be taken to an input where we can generate our TXY, PXY, as well as some other ones. And it's just as simple as choosing which one you want. So in this case, I'll go with PXY. And you can even list different values of temperature. So if I wanted to look at 40 or if I wanted to look at 5, I could run that. And it'll just generate that for me. So you can very quickly and easily make your TXY and PXYs, which will be pretty useful later on for distillation. So something I did want to check. Forgot the other component. Let's see, I want to see if I could get an azeotrope. And here we go. So I did this between acetonitrile and water. And what I wanted to show you is an azeotrope. Benzene and toluene is very nice, so we don't have an azeotrope, but here we do, which means that separating this is going to be pretty difficult. I ran it at different pressures, with this bottom one being at 5, the middle one being at 25, and the top one being at 40. We can see that this azeotrope is going to be kind of our maximum limit for our separation that we can get in these conditions. So as we lower that pressure, we can see that it starts to move further to the right, which would allow us to get a higher purity. You can also adjust temperature, and sometimes there's just only so much you can do, so you'll actually have to just make a chain of units, usually a chain of distillation columns, to just keep further and further refining it to where you just boost your purity to where you want it to get. So once you've looked at everything that you want to look at here, you can now move to your simulation section. This is where all of your work is actually going to be taking place. At the bottom here, we have a bunch of different units for whatever we need. And this box here is just to draw actual streams of materials. So first we could look at separators. This is where you'll find your flash unit. The one we usually use in senior design is flash 2. So you just click on that and click anywhere on it, and it's there now. But now we have to add streams to it. Everything's going to need to have an input and an output. Usually with flash 2 and distillation columns, it needs one input at the minimum and 2 outputs at the minimum, but you can have more depending on what it is. So at our input stream, at our top, at our bottom, you can right click to get off of that stream button so that you can click on things normally. And usually you want to be in the habit of naming things, because what we're going to do is after we run this, we're going to open up a results thing that's pretty much a massive table. And while we only have 3 here, whenever you're working in it in the future, you can easily have like well over 20 that you're looking at and comparing. So you want to be able to have good names for all of them so you know exactly what you're looking at. Let's go liquid. And you can also name the actual units themselves. So the first thing we need to define is our actual feed stream. And what I'm going to do is, if you go to the top left, you can change the default units of everything. I prefer to work in the English unit set. So let's say we want to just run it at room temperature and at atmospheric pressure. You can do your flow rate basis either on mole or mass. I personally prefer to do mole, but that's really up to you and just whatever information that you're actually given. And what this is on the right is where we set the composition. You could do mole flow, mass flow, or fractions. I prefer to do mole fraction. So if we wanted to look at acetone and water, which flash units are, let's see, flash units are like a single stage pretty much of a distillation column. They're really good for separating things, like if, for example, if you have a stream that has liquids and gases, those are where your flash units are really ideal. Otherwise, you'll typically want to move towards using a distillation column. But if you have something where like the boiling points are drastically different, where it's very easy to separate it, it's a good choice, but otherwise you're probably going to be using a column. So for this, I chose to use water and acetone because they have very different boiling points from each other. So if we run it at just room temperature, which acetone will evaporate quickly, but it's usually liquid at room temperature. And it looks like I actually missed something because it's showing me it's red. I need to do the actual inputs for the flash drum. These are the conditions that we'll run it at. We can run it based off of temperature, vapor fraction, or heat duty. For example, if we ran it off of vapor fraction, we can decide how much of it we want from that initial flow to actually come out the top, and it'll do all the rest of the calculations to figure out what conditions we need to run it at. Sometimes that can be useful, but other times it doesn't give you exactly what you want. So let's run this at pretty much ambient temperature and pressure and just see what we get. So now everything's good, required input's complete. So I can go ahead and run it. And the results are available. So we can right click on it and see stream results. If you click results, it'll show a different screen related to the actual performance of the unit instead of showing you where everything is. So typically you want to go to stream results, and it'll give you basic information about everything, the temperature, pressure, and we can already see that there's nothing coming out of the top. For our mole flow rate, everything's just coming out of the bottom. So we're going to want to move to a higher temperature. So if you have a rough idea, you can start just increasing the temperature. But if you don't know, that's where we can just make a diagram for them. So with our PXY, you can see that increasing the temperature gives us a bigger region. And if we do TXY, we can see that a lower pressure would also give us a better separation. So if we go up to maybe 140, we're still not getting anything out. So let's go to 160. And now we're starting to actually get some separation. And this can be fine-tuned just by messing with the temperature and pressure to get the exact conditions that you want. However, distillation column will give you a lot more customization because this is like one stage of it, while distillation column is many different points of equilibrium. So now that we've looked at our flash, we can start looking at columns. So the column that we're going to be using is radfrac. That's the one that's typically always used whenever you're in senior design. And the streams that are required are your feed stream. You have to have a bottom stream, which is going to be a liquid. And for the top where you have your condenser, you can either have a liquid stream or a vapor stream. Typically, you're going to go with a liquid stream just because gases are usually harder to work with. And once again, I'm going to name my streams. And name my column. Now I need to define my stream, which this time we're going to be looking at benzene and toluene. And we're just going to do a simple 50-50 split. At ambient temperature and pressure. And now we need to actually define the conditions for our column. So for the column, we're going to have to do the configuration, the streams, and the pressure. So typically it's good to start with about 10 stages. In your senior design, you're usually going to be limited to no more than 40 stages unless you're under special conditions. And the reason for this is just that you can always add more stages and get better separation from your column. But as you add more stages, your column's going to get taller and taller, and it's going to get bigger and bigger, and thus more most expensive or more expensive. So your first section of senior design is going to be making everything work. Your second section is going to be making everything cheap. So that's one of the limitations that you're going to be placed on. For the condenser, we're going to do total. that's where everything is going to be condensed to a liquid. If we had one of those vapor streams, and we could do partial vapor, if that's just vapor, or partial vapor liquid, to where we could have a vapor product and a liquid product in our condenser. But we're just going to be looking at total. The reboiler will usually be kettle, and everything else will usually be the same. So we could define our distillate rate and our reflux ratio. We could also define a bunch of other things. But in this case, we know that we have an even split, and I chose 10 pound moles. So I'll just do 5, and hopefully we can get everything. For your reflux ratio, this is pretty much how much is going to be going from the condenser unit back into the column. The higher that this is will usually result in a better separation, but it's another thing that'll make your unit more expensive. So there's usually going to be a limit on that. But in senior design, you're usually going to start with 3. And that's one of the last things that you want to change if you can. Next is streams. For this, we only have one feed, and we need to define where that is. Usually, you want to start just in the middle. So I'll just go with 5 since I chose 10 stages to start out with. And then lastly, we need to choose the actual pressure of the column. So for this, I'll just go with ambient pressure just to be sure. I'll put it in ATM. And it shows that I still need something else. I'm not done with my input because I didn't actually put the flow rate. Now it says input changed, which every time after you run the simulation for the first time, instead of getting the required input complete, it's usually going to say input changed. So we can go ahead and just run this. And our results are available. Fortunately, everything is converging. This will usually run off of a bunch of iterative calculations. And whenever your actual flow chart gets more complicated, that's where you start running the issues of having things not converge, where your numbers, instead of just being guesses, need to be really, really good guesses. Otherwise, you could just break the whole thing. But fortunately, that didn't happen. So we can look at how we did. And because I set that distillate flow rate to 5, it's going to be exactly 5. And same for the bottom, since it's going to be split evenly. But we can actually look at our purity. And so far, it's actually pretty good. We're already at 95% purity, which a lot of the time, you're either going to want like 95 or 99, sometimes higher than that. But most of the time, 95 is pretty good. But say we wanted it higher, then we could do a few things to actually get it higher. So another form of results that we can look at under this column design tab is the composition. So here we can look at either the vapor or liquid. We can select all, and I'll select both. And we can see through each individual stage what the actual composition looks like. So we can see how smooth of a curve this is. And you typically want it to be smooth. There are things that you can do that will make it not smooth. For example, if I went back to my column, based off of this, it really likes having the feed right in the middle. But for example, if I move the feed all the way to the bottom, so you put it at 10 and run that. It seems to actually not mind that at all. So we can check our steam results. We can see that purity is a lot less though. And we can see it here as well. Stage 1 is the very top of the column. Stage 10 is the bottom of the column. So at the top, our purity is less than 85. And for the top, that's where we want to be looking at the liquid. In fact, because both of our products are liquid, it would be best to look at just the liquid. So if we wanted to fix that, we could move our stage back up, but we could also just put our stage really high. We can put our feed really high up in the stages to also just see how that affects it. And now we can see that there's a very sudden bump in it. It doesn't like being right there. So whenever you no longer have a smooth curve, that's a sign that you need to move your feed somewhere lower into the column or higher. So we can take our feed and put it back at 5. And we could also just add another 20 stages. We know that our feed needs to be in the middle, so we'll put it in the middle here. So this time it'll be at 10. And before we had our purity at about 95. This time we're at 99.7. So with these columns, there's a lot of different things that you can do to further increase your purity. You can adjust the number of stages, the reflux, the distillate flow rate. There's a lot of different customization that you're going to have to do. But that's pretty much the basics of it. Are there any questions? I know I kind of went pretty quickly. All right. And with that, I will stop sharing.